Okay, so we are going to conclude the course of arbitrage theory by some consideration concerning American options. Okay, so what I will do first will be to give you general consideration on American options in discrete time models. Okay, and I will also do a numerical example. Okay, in the case of the binomial model I have just seen in the previous video. And the idea is to try to convince you that to price a European option in this kind of model is not simpler than to price American options. Okay, so let's do the job. So let's start from the beginning. Okay, so it's the part concerning American option. Okay, so just a remark before to start with the definition of what is an American option and what is the difference with things that we use to work for the moment. Okay. Previously, we have defined what was a contingent claim. In my framework, I keep the framework of the first session. So a contingent claim was just, okay, a random variable that was F capital T measurable. And I have said that intuitively, it represents the payoff of an European type option. Okay, describing what will happen at capital T if you exercise the contract, okay, or not. You have the possibility not to exercise, okay, so it's this. So in my situation, okay, to describe, let's say, a European contract is done through the notion of an F capital T measurable random variable. Let's see the definition of an American option. Here, an American option will be for us a non-negative discrete stochastic process. So non-negative is not that necessary here. Okay, so I can erase, okay. An American option is a discrete stochastic process that is adapted to my filtration. Okay, so an American option is not a single random variable anymore, but a stochastic process such that xt hat is ft measurable. I want an adapted process. Okay, so what is the financial interpretation of this one? Okay, so in the case of the contingent claim, B hat represent what will happen at capital T if you exercise, okay, so what you obtain at capital T, okay, if you exercise or not your European type option. Here, in the case, so, and you know that for European contingent claim, you can only exercise at the maturity of the contract, that is here, capital T. For an American option, you will have the possibility to exercise at any time between 0 and capital T, okay? And in fact, as I have written here, xt hat will represent what, if you are the owner of the option, what you will receive if you exercise at time small t. Okay, so xt hat is what you will obtain if you exercise at time small t. So I see that there is a big difference between contingent claim and American options, because from a mathematical point of view, one is represented by a single random variable that is F capital T measurable, and the other being, okay, a stochastic process. So an American option, a priori, is more and more complex because instead of using a single random variable, you need a stochastic process, okay, defined at any time in order to describe what happens if you exercise, okay? So from now on, okay, to study this kind of product, okay, we are going to suppose the following. So I suppose that I have a single risky asset, okay, so I have one risky asset here and only one. Why not? Okay, and I will suppose, so here I have forgotten something, that the set of the equivalent martingale measure here is just reduced to a singleton, meaning that I want to work in the case of a complete market. If I am not complete, it will be more complicated to deal with these options. Okay, I will restrict my case, myself to the complete case. So let me give you example of such American options here. So as example, it's a process. Okay, so I can have, for example, this one. And you have here what we call an American call option. An American call option. Okay. You have also, in the same way, an American, the plus here, the maximum between this one and 0. An American put. Okay. The first question I want to answer is it possible to replicate an American option? In the case of contingent claims, so I remind that here I have a single element, so my market is complete. So when I have a contingent claim, if my market is complete, and it's exactly what I have as an hypothesis here, there exists a self-financed financial strategy such that its final value, or I write the thing in the actualized way here, is equal to capital B. Okay, so I am replicable because my market is complete. Okay, so I have the possibility to replicate exactly. Okay, and I have remind that the arbitrage-free price process, okay, fulfills in this situation this basic form the conditional expectation of the actualized payoff with respect to the unique equivalent martingale measure. Okay. My question now is it possible to replicate an American option? So here, in the case of the contingent claim, replicate means that I want to be able, using the market, okay, to reproduce at capital T my contingent claim. Okay, final value is equal to B. In the case of an American option, so if I write it in the actualized way, so if I have my American option, it is replicable if there exists a self-financed strategy. But here, in order to be replicable, I need to have Vt equal to Xt for all t belonging to 0 capital T. So something that is more and more restrictive than just to have a final value equal to capital B. Here, I want that at any time, the value of my strategy is equal to the payoff of the American option here written in the actualized way at any time, okay? But why it's not possible to have this in general? Because I know that under Q, VT is a martingale. I know this because, okay, if I am a self-finance financial strategy, my actualized value is a martingale under Q. It's something that we have proved, okay, in a previous session. So I have this, but why it is in contradiction with what I want? Because XT is not a Q martingale in general. So there is no reason for XT to be a Q martingale. So typically, if I come back to the of the call and the put option, okay, there are no reason that the actualized value of these processes, okay, are martingale under Q. In general, it's not the case. I have the martingality of the actualized value of this quantity here. It's the risky asset, but not the one of the payoff of such options. So in general, we won't have the possibility to replicate perfectly an American option. So it means that if I want to price this one, okay, I have to adopt another approach. It's not possible to define the price as the replication price as we have done for contingent claim. Okay, so we are going to adopt another point of view for an American option, and it's what we call, okay, the backward induction reasoning. Okay, the backward induction reasoning, and it's what we are going to see now. Okay, I have this proposition, the first one. I denote by UT at the price of my American option. And I say that this UT at fulfills the following, okay? First, that U capital T is equal to X capital T, okay? And the fact that I have a recursive relation between UT and UT minus 1 that will allow you to obtain from the end to the beginning, okay? Using this recursive equation, you will be able to, starting from the end, to obtain, if I use this relation with capital T, okay, I will have U capital T minus 1 from U capital T and X capital T minus 1, okay? And I know X capital T here, that is U capital T. Okay, so it's a recursive way in order to price the option. So let's see why we have this. If I am at capital T, I don't have the choice. I won't have the possibility anymore to exercise as at a date after capital T, because capital T is the maturity of my contract. So necessarily at capital T, okay, the price of what you have will be what you obtain if you exercise the option at capital T. Okay, so I said that in fact U capital T at is necessarily equal to what you obtain if you exercise at capital T, because you don't have exercise before, okay? And in this case, my American option is none other than a European one, okay? I am at capital T, and at capital T, when I am at the maturity, there are no differences between a European and an American option because I have only the possibility to exercise or not at capital T, okay? So, X capital T will be what I obtain, okay? in this case, if I exercise. Okay, so I have this one for capital T. What happened at capital T minus 1? So at capital T minus 1, okay, it's a little bit different because, okay, at capital T minus 1, I can decide to exercise or not, okay? And I will have the possibility to exercise later at capital T, maybe, okay? So I have here, I have two cases. The first is the case where I decide to exercise at capital T minus 1. If I do this, I obtain what? I obtain x capital T minus 1 at. I obtain this one, okay? I obtain x capital T minus 1 at if I exercise at capital T minus 1. It's what I obtain if I exercise my American option at capital T minus 1, okay? What happens if I don't exercise? If I don't exercise at capital T minus 1, okay, I do nothing at capital T minus 1, but I know what I will receive at the end. I will receive x capital T at time capital T. I will receive x capital T at capital T. And what I want to know, in fact, is what is the value of the product that will allow me to obtain x capital T at capital T. And according to what I have done previously, and using the fact that my maquette is complete, okay, the price at capital T minus 1 of a product giving x capital T at capital T is just the price of a one period contingent claim, okay, a European option if you want, okay, and the price of this one, okay, the value of this quantity at T minus 1, so the actualized value, in fact, okay, or the value, if I want to write the value, is what, okay? So I know that, okay, if I have a contingent claim, the price at T minus 1 of my contingent claim is given by this. I have this one, okay? It's the actualized value, typically a T minus 1 at, okay, is equal to what? Is equal to S0 capital T T minus 1 expectation under Q of B at over S0 capital T at given F T minus 1. And here, in fact, I just have to use this formula for B equal to X capital T at. And if I do the job, the value at this quantity at time T minus 1 is this one for B equal to X capital T at, that is S0 T minus 1 expectation under Q of X capital T at, okay, over S0 capital T at given F T minus 1. So I have this. So it means that at time T minus 1, if I exercise, I obtain this. If I don't exercise, I have something that has this value at time T minus 1. That will be the possibility to exercise at capital T. And so what will be the price of my American option in this situation? So if I exercise, I obtain this. If I don't exercise, I obtain this. So it means that if you are the owner of such a product, okay, you don't want to pay more to have this option than the best case you have here, okay? Because the best you can do at time t-1 is the maximum between these two quantities, and you won't accept to pay more, okay, to have such a product. Contrary to the point of view of the seller of such product, a seller won't be able to sell at a price that is lower than the maximum between the two, okay? Because it will be what it will have to give you if you exercise at capital T-1. So from the point of view of the owner, you can't be greater than the maximum between the two quantities here. From the point of view of the seller, you can be less than the maximum of the two quantities. So the price will be exactly the maximum between these two quantities. The price at time t-1 is, okay, this one. Okay, so you have ut-1 at, that is given by this quantity. Doing my exercise here, I exercise or not, and then I take the point of view of the seller and the point of view of the buyer of the option. Okay. And if you do exactly the same at the other dates, if you do exactly the same at the other dates, you can obtain, as a generalization of what I have done here, for any time t less than capital T. In fact, what I will have is the following, that ut-1 at, okay, so do it. You can do it by induction, or you can do it just reproducing the reasoning I have done here, will be what? But the maximum of what you obtain if you exercise at time t-1, you obtain xt-1. And if you don't exercise, you will obtain something that will have a price ut at the date after, that is at time t. And so you have here S0 t-1 at expectation under Q of here ut at over S0 t at given ft minus 1. I repeat that the way to obtain this, is just to say that at time small t minus 1, if you exercise, you obtain this. If you don't, you will have a product, okay? This one has a value that is ut at time t, in fact. Okay, this is the value at time t-1 of something that is equal to the price of the option at time ut at. Okay, so I have this one. I can express this quantity in an actualized way. So here I have quantities at time t-1, t-1, and t-1, okay, here. So if I actualize these quantities dividing by the value of the non-risky asset at time t-1, I obtain ut-1 that is equal to the maximum between xt-1, so this one disappears, the expectation under Q of what? This one is none other than UT, in fact, given FT minus 1. And you have, so this nice expression that is a recursive expression in order to express what can be the price of an American option. I'll do an example in a few minutes here in the case of the binomial model. The price of an American option can be obtained starting from the end because, okay, you know what is this quantity. This quantity is known here. It's the payoff at capital T. And in order, so you have the price at capital T, and in order to obtain price at time that are before capital T, then you use, okay, from the end to until T minus 1, this recursive formulation here. Okay. So this is the proposition giving to you the price of an American option. And you have this nice, okay, formula when you write it in the actualized way. Okay. So before to show you an example, okay, we are going to see one little, in fact, two little properties, okay. I said that, in fact, the actualized price of an American option is the smallest Q martingale that dominates this American option. So UT is the smallest Q martingale such that UT is greater than XT. By dominates here, I mean, okay, UT greater than XT. So if you want, okay, it's the best thing that you can do if you want to approximate xt at any time by a Q martingale. Excuse me, it's not a martingale here. So I have done a mistake in the slide. So it's not a martingale here. It's not a Q martingale. It's a Q super martingale, not a martingale. Huh? Super martingale, not martingale here. Be careful about this. Okay, so if I come back to what I know for contingent claim, I know that I am able to replicate, and so that the price is the price of any financial strategy that replicates, okay? And in fact, you can define this way, the price at any time as the value, and the value is a Q martingale in this case, with a final value that is equal to B. Okay, so the price is given by a martingale. So the actualized price here is a martingale in the case of a contingent claim, a Q martingale with a final value that is equal to capital B. In the case of an American option, it's not possible for me to obtain such a thing, okay, as I have explained at the beginning. But I see that by my previous reasoning, I observe, and I will prove this proposition, that the actualized price is not a martingale anymore. It's a Q super martingale. And the condition is not that Q capital T is equal to B as in the case of contingent claim, but UT will always. So we are going to prove this proposition here. But just before, I want to do a little work. Okay. So let's do this. So I will start just after the proof of the proposition, that is a basic one. A little remark before to do the proof. I said that UT defined this way is always greater than this one. Okay, so why I have this? So you can do it in several ways, okay? But one way to do is to do a backward induction once again, okay? So what happened for capital T in this expression here that I call star? I have here U capital T, and you have here, because small t is capital T here, X capital T. And in this case, by definition of U, I know that I have equality, okay? So my relation star is okay for capital T. So now suppose it for T and prove it for T minus 1. Okay, so we do a backward induction here in order to prove this quantity. I start from the end and I prove that if I have it at the date, I will have it at the date before. So if I have it for T, I have exactly what I want here. And I am interested in what happened for ut minus 1. But what I know that ut minus 1 is equal to the maximum between xt minus 1 and the expectation under Q of ut given ft minus 1. So you have something here that is greater than the expectation under Q of ut given ft minus 1, okay? Using my induction hypothesis here. So this is my induction hypothesis. Then, okay, this one is greater than the expectation under Q of the conditional expectation of xt given ft given ft minus 1. And since ft minus 1 is included in ft, using the tower property of the conditional expectation, I see that here I have simply this one that is exactly to prove this one at time t minus 1. So here I have proved by backward induction that ut is greater than the expectation under Q of x capital T given ft. But what is the meaning of this here? Of the price of the American option. What is this? Here, in fact, this one is just the arbitrage free price at time t of the corresponding European option. So what we have proved here mathematically is just the fact that the price of an American option is greater than the price of the corresponding European option. Of course, okay, I consider that they have both the same maturity, that is capital T. Okay, so I recover, okay, from property of conditional expectation, the financial fact that American greater than European in terms of price, okay, because, okay, an American option give you more possibility than European one, okay, so it is a product that is, okay, more expensive. Okay, so I have done this remark here. Do this. I will erase what I have done here in order to do the proof of my result here. Okay, I want to prove that U is the smallest Q martingale that dominates xt. Before to prove that I am the smallest Q martingale that dominates xt, before I prove that I am the smallest, I have to prove that I need to be 1. So what I have, take what you have here. Okay, you have ut minus 1 that is equal to the maximum between these two quantities here. So you have at the same time ut minus 1 that is greater than xt minus 1 because it is greater than the max, and ut minus 1 that is greater than the expectation under q of ut given ft minus 1. So you have here the fact that you have a q super martingale. You have a q, you are here a q super martingale. Okay, it's exactly the definition of being a super martingale here. And here you have the fact that u dominates x because it is always greater. Okay, so from the definition you obtain that ut, the actualized value of the price, is a q super martingale that dominates xt, and I want to prove that it is the smallest. Okay, so in order to prove that it is the smallest, we are going to consider another one and prove that my u is smaller than this other one. So let capital T of small t, t belonging to 0, capital T, so such that, okay, it is a q super martingale, and t of t is greater than xt at any t. Okay, and I repeat that what I want to prove is that t of t is greater than ut for any t. Okay, and once again we are going to do the reasoning starting from the end. Okay, so at capital T, what happened? At capital T, I know that capital T, T of capital T is greater than xt. But at capital T, I know that x capital T is equal to u capital T. So I have proved this relation for small t equal to capital T. Okay, so I have this one. Let's continue. At time t minus 1, okay, what I have? I have, of course, that capital T minus 1 is greater than x capital T minus 1 by this property here. But I can use the fact that I am a super martingale also, q super martingale. So capital T at time capital T minus 1 is greater than what? The expectation under q of, capital T given ft minus 1, because I am a q super martingale. Okay, it's this one that I use here. But from the previous step, I know that this one is equal to the expectation under q of u capital T given ft minus 1. And then what I have that capital T of t minus 1 is greater than this one and greater than this one. So it is greater than the maximum between xt minus 1 and the expectation under q of ut given ft minus 1. And what I recognize here, I recognize that this expression here is exactly what you obtain here for capital T, or for small t equal to capital T. So I have here u capital T minus 1. So it means that at time capital T minus 1, I have proved my relation. And you can continue. And if you want to do it properly, you can try to continue my reasoning here. I won't stop, if I will stop here. Okay, but doing a backward induction. Suppose that it is true at time t and prove it that is true at time t minus 1. Okay, and what you will have will just be to use the Q-Martingale property and the induction hypothesis. Okay, so I have a characterization. So in the case of contingent claim, the price is a Q-Martingale with a final value equal to my contingent claim. In the case of American option, the price is the smallest Q super martingale that dominates the process, the American option process. Okay, so I have this. Okay, so before to see my numerical example, okay, I want to show you a result. So a result that you probably know, okay, because it's something that we can prove, okay, without mathematics, just using, okay, absence of arbitrage opportunities, okay, that is the following. So if you suppose that the non-risky asset is deterministic, okay, meaning that, okay, S0t hat is a function of t, not something that is random, okay? And if I suppose it increasing, so here, just be careful, I have done a misprint here, it's end, okay, not ends, deterministic and increasing here, then I said that it is never optimal to exercise an American call option before capital T. It is never optimal to exercise an American option, an American call option before, strictly before its maturity. Okay. So if you are fluent with classical reasoning of arbitrage without mathematics, okay, it's not that complicated to prove that if you exercise before, it's always possible to exhibit strategies, okay, that are better than to exercise, okay, that are better than to exercise. Sometimes it will be, okay, to sell the option itself, okay, or keep it until the end, okay, in order to use the fact that you can capitalize. But here, it's not this kind of proof that we are going to do. We are going to do a mathematical proof of this one, okay, using a key result that will be the Jensen inequality. Because in fact, keep in mind that the payoff of a call option is related to this mapping here. Plus, if I plot it, I obtain something like this. So if I have my K here, I obtain something like this. Okay, it's the classical payoff of a call option. And here I have a mapping, and it will be the argument that I will use that is convex. So it will be possible to use the Jensen inequality here. And in fact, I have state the proposition for call option, but you can replace this assumption to be a call by any American option associated to a convex payoff, in fact. Okay, any American option that is associated to a convex payoff, I have this one. So it is never optimal to exercise an American call option, but okay, any American option with a convex payoff. And what is the meaning of this one? So if it is never optimal to exercise before the maturity, but then the only possibility you will have will be to exercise or not at capital T. And so in this case, your American call option is none other than an European one, okay? And so that's why I have this expression here, because if it is never optimal to exercise before, in fact, American is equal to European, in this case. And so the price of my American, the actualized price of my American is this quantity that is just the price of the European option. Okay. So in this situation, I have this, okay? And you will see that the key argument will be a convexity argument. So let's do the proof of this proposition. It's not that complicated if you have in mind that convexity is what you are going to use. So suppose the contrary. So suppose that it is optimal to exercise at small t strictly greater than capital T. Okay, I said the following. So if it's optimal to exercise at small t, it means that what you will obtain when you exercise, so what I will obtain, if I write it in the actualized value, what I will obtain if I exercise, okay, is this one. What I will obtain if I exercise is exactly xt, that is equal to st at minus k plus over S0 t at. Okay, so I can write it. What I obtain when I exercise at small t. So what you will obtain if you exercise at small t here is in fact strictly greater than what you will obtain if you don't exercise. But I know what I obtain, okay? So what you obtain here, it's at time small t, at small t if you don't exercise. So if I don't exercise at time small t, it means that I will have one period later, okay, the price of this option at t plus 1 here. So the price of such a product is the expectation under Q of u t plus 1 given ft. Okay, so keep in mind to what I have proved previously, okay, maybe this slide here. You have here the definition of the price, and the price is the maximum between what you obtain if you exercise and what you obtain if you don't. Okay, so it's exactly what I have written here. In green, it's what I obtain if I don't exercise. Okay, so I have this one. So what I know that ut plus 1 is greater than x plus 1, xt plus 1, excuse me. Okay, by definition of u, what I have proved, u t minus 1 is equal to the maximum between xt minus 1 and some 1. So ut minus 1 is greater than xt minus 1, of course. I dominate xt. I dominate it. So this is greater than the conditional expectation under Q, okay, of xt plus 1 given ft. And I know what it is, this one, okay, it is what? It is the conditional expectation under Q of, so xt plus 1 in the case of my American call option is st plus 1 at over S0 t plus 1 at minus k over S0 t plus 1 at plus given ft. And it's here that we are going to use the Jensen inequality for conditional expectation. Because the payoff of my European option here is a convex mapping, so you know that the conditional expectation of the image of my random variable will be greater than the image of the conditional expectation. Okay, it's Jensen inequality that tells you that if we have phi that is convex, okay, you can write it this way. The conditional expectation under Q of phi of x given something is greater than phi of the conditional expectation under Q of x given f. It's the Jensen inequality for, in fact, conditional expectation or for expectation simply. So what I obtain here, I obtain simply applying this one to the mapping, okay, phi given by the payoff. It is equal to the following. So I am greater than the conditional expectation under Q of here. I have this one that is ST plus 1, okay, given ft minus k over S0 t plus 1 at plus. But what is this one? Don't forget that Q is an equivalent martingale measure. So here, what I have, I have simply ST minus K over S0 t plus 1 at plus. At the end, what I have obtained, I have proved that this quantity here, where you have, in fact, here, I have here simply ST. Okay, this quantity is greater than this one. It implies that, so I have ST minus K over S0T at here, and here I have ST minus K over S0T at, and so I have that minus K over S0T at is strictly greater, okay, than minus K over S0T plus 1 at. If I have this one that is greater than this one, okay, it implies that minus K over S0T at is greater than minus K S0T plus 1 at. And I have a problem with this. I have a problem. It's not possible to have this. Why it's not possible to have this? Because I have supposed that my risky asset is increasing. And here, if I have this inequality here, it implies that S0 t plus 1 at is strictly less than S0 t at, something that is not possible. So what I have supposed at the beginning is not true. That is, it's not optimal to exercise before capital T strictly. And so an American option is in this situation none other than a European one. Okay? So that's why in the next example, we are not going to price American call option, because I know that in this situation, it's none other than the price of the American put, the European call, excuse me, but we are going to price American put option. Okay, so it's exactly the aim of the next slide here. So this one I can erase. I don't need it. And I have this one. So it's an example. Okay, so what I will do here, okay, I want to price in. So what is the situation? But the situation is the one that I have treated in the previous video. That is the binomial model with 3 periods, okay? A U that is equal to 1.1, D that is equal to 0.9, R that is equal to 1 plus the logarithm of 1 plus 0.0.5. So I have here exponential R that is strictly greater than D, strictly less than U, meaning that according to what I have done, I have no arbitrage in this 3-period model, okay? We have also proved together that this model is complete. This model is complete, and in particular, okay, I can find the equivalent martingale measure. The equivalent martingale measure, remind that we have seen together that Q of WU in this situation is equal to Q of W1 WU, that is equal to Q W1 W2 WU. I have done the computation here. It was 3/4. In the same way, Q of WD for this model was equal to Q W1 WD. That was equal to Q of W1 W2 WD. That was equal to 3/4. Okay, so if I denote this one by Q, it's 1/4, of course. I need to have a probability. So this one is, of course, 1 minus Q. And here, okay, if I write the risk neutral probability, I have Q1 minus Q, Q1 minus Q, and so on for all of them, okay, until this one. And here I am in the situation where all the conditional risk neutral probabilities are the same, up with probability 3/4, down with probability 1/4. Okay, and you have here in the tree, you have what? You have the dynamic of the risky asset. So in black, the value of the risky asset, the unique risky asset, and in red, the actualized value of the risky asset. Okay, so just a remark here. So what I want to do, so let's pass to the next slide, okay, to make this clearer. So we have this one here, so let's pass to this one. Okay, so maybe I will try to make it a little bit bigger. Excuse me. I put it as big as I can, okay, that is this one here. Okay, so if I want to price my American option, so keep in mind that I have U capital T that is equal to X capital T, and I have U T minus 1 that is equal to the maximum between X T minus 1 and the expectation under Q of UT given FT minus 1. So if I want to find explicitly UT, it's my job here, I want to price. So I want to price what? Okay, I will explain what I will price. I will price a US put option with maturity capital T is equal to 3 and a strike that I will take equal to 20. My strike equal to 20. Okay. I want to price this put option here. I want to price it. If I want to price it, I need to know this one. I need to know this one because, okay, UT minus 1 will be the max between this conditional expectation that will compute backward, okay, and this one. So I need to do the tree for xt, where xt here is simply st minus K over S0 T at plus. So excuse me, it's a put, it's not a call. It's a put, it's not a call, so I don't have a minus here. I have a minus here, and I have a plus here. Okay, it's a put option I want to price here with K equal to 20. So you see that if I want to compute these quantities, I will have to compare them with what I have in red here that are the actualized value of the risky asset, okay, and compare them to this one. So just to make you sure, okay, I have K over S00 at, that is in my model 20, okay, and I write you what are the other quantity, S01 at, for this one I will obtain 19.05, K over S02 at, I obtain 18.14, and the last, that is K over S03 at, will be equal to this one. And why I compute these four quantities? Because it's the one that are involved, okay, to compute x3, x2, x1, and x0, okay? And then I have to do what? Okay, I have to consider the part between the maximum between this difference and 0, okay? Knowing that the dynamic of ST is given by the tree in red here, okay? And I have these values for, okay, the four possible cases. So if I do the tree in this situation, I do it, okay? And I obtain 0, 0, 0, 1.9, 0.18, 3.45, 0, 0, 0, this one, and the last, that is 4.69. Okay, so you have everything to compute. I repeat, ST is given by the tree in red here, and all these ones are given by the numerical value I have given to you here. Okay, so I obtain 0, 0, 1.989, 4.69, and these quantities for time that are strictly less than 3. Okay, so what I want to obtain, it's UT. Okay, and first of all, I know that at time capital T equal to 3, UT is equal to x3. So U3 is equal to x3. So U, I can build the 3 for you, 0, 0, 1.9, 4.69. I don't have the choice here because here you have U3 that is equal to x3. And then I have to complete the 3, okay, to obtain here quantities that I will denote as in the lectures note 1, 2, 3, 4, 5, and the price at time t equal to 0, that is 6. And my job is to determine all these quantities here, is to determine all these quantities from the trees I have here. Okay, so let's do the job. Where I am here, just to be sure, I am here. Yeah, so I duplicate this page, I reduce, and maybe, I don't know if I can, no, I can't do this one, so I will do this. Because in fact, for my video, I need only, yes, to have these two trees here. So let's do the job. Okay, I will do the job for some of them. Okay, I will do for all of them, but What is 1? So keep in mind that ut minus 1 is equal to the max between x t minus 1 and the expectation under q of ut given ft minus 1. Okay, so to compute u, I use a backward induction. I know u3, from which I will be able, since I have u3 and x2 here, I will be able to have u2. Then if I have u2, I will be able to have u1. And then if I have u1, I will be able to have u0 here. Okay. So what is 1 here? 1 is just the max between, so it's, okay, the max between x2 wu, the expectation under q of u here 3 given f2 wu conditional expectation under q, of course. Okay, but what I have here, this one is 0 because of this one. Okay, so it is equal to 0. And what is this conditional expectation here? Okay, this conditional expectation is what? It's the conditional expectation under Q, okay, of something that has a value 0 I times 3, okay? So in fact, compute this conditional expectation here will be, so keep in mind that for Q, I have 3 over 4 here, I have 1 over 4, and so on, okay? So 3 over 4 here, 1 over 4 here as a probability. So this term here, this one, is just the conditional expectation computed on this little model of size 1 here, that is q times 0 plus 1 minus q times 0. So this one is also equal to 0. So 1 is equal to 0 because it's the max between 0 and 0. What is 2? 2 is what happened here. So it's the max between, so 2, it's WUWD. X2 WUWD. So what is x2 of WUWD? x2 of WUWD is 0.18. And then you have to compute the conditional expectation of U3 given F2 at the point WUWD. And what is this one? So it's the conditional expectation of something that has these values here. So it is this term here is equal to 3 over 4 times what? Times the 0 here, plus 1 over 4 times this term here, 1.89. This quantity is equal to, so I have WUWD, okay, WUWD, so it's what I have done here. So 0.18, and this one, so just, okay, I just want to be sure that it copes with what I have done in my my lectures note, okay. So let me once again to do the job. So 2, okay, so yes, it's exactly this one, excuse me. So I obtain here, okay, this quantity that is equal to 0.47, okay, and I obtain 2 that is equal to 0.47 because it's the max between the two quantities. Okay, so you will have more details on the computation in the lectures note, and here I just give you the result, okay, because I have done it for 2, okay. it remains to do it for 3, where you will obtain, okay, what 3.45, that is the maximum, okay, so 3 is what happened at WD, so it's the max between this one and the conditional expectation of this random variable here, okay, that is 3/4 times this one plus 1/4 times this one, and the max keep this one, and so on, okay. So for 4, you have 0.12, and for 5, I obtain 1.91, and for 6, I obtain 0.57. Okay, so you have here priced an American put option, okay, in a 3-period binomial model, and you see that the backward induction reasoning is in fact not very different. So you just have 2 trees to build, contrary to what happened in the case of a contingent claim when I have a single tree to build. But here, in fact, it's not that more complicated. So with this kind of models with trees, okay, the pricing of American options in discrete time is not more complicated than the pricing of European contingent claim. And the interest of such model is that, okay, here it was just an example to be able to do all the computations. But if you do this with a model with a large number of periods, okay, and with a good choice of U and D, okay, you may have a dynamic that is not that unrealistic to obtain this. Okay, so it concludes the part concerning the numerical example, okay. And now, in order to conclude, what I have here, okay, in order to conclude, so I want to do a little comment. So you can consider this as out of program for the final exam, okay. So maybe I will just do a 5-minute break, okay. So I come back in 5 minutes. Okay, so let's continue what I have starting to do here. And the idea was to, okay, excuse me. Okay, this one. The idea here, okay, is to make, so it's something that will be out of the program of the final exam, okay, as I have already said. It's the definition 15, not the definition 1514, okay. And it makes the link between a notion you have seen in the course of stochastic calculus in continuous time with Mr. de Meyer, that is the notion of stopping time, and the problem of the American options, okay. So it's not particularly related to what I have done before. It's more intrinsically linked to what happened for American options, okay. But we can make some links, okay, with the problem of the evaluation of American options and the problem of finding good stopping time. So what is a stopping time? So a stopping time, okay, will be a random variable. It's a random variable here from my universe omega with values in my possible dates, okay? It's the set of the dates here. And this is a random variable that fulfills a property, that is the fact that tau equal to t is an element of the sigma algebra ft, okay? So tau equal to t belongs to ft. So what is the meaning of this one from a financial point of view? So be careful, it's not the notion of being adapted, it's something that is different. I don't have a stochastic process here, I have a random variable. And I just say that the fact that the set on which this random variable take the value some the value small t, has to belongs to my sigma algebra of financial information at time small t. So what is the meaning of this one? So come back to the problem of the American option. When I buy an American option, okay, my problem is when I can exercise this American option. Okay, so when I am at time t equal to 0, but my strategy will be at time t equal to 0 random, because I don't know at time t equal to 0 what I will do in the future, because I don't have the financial information that will be available at the future. Okay, but if I want to make the notion of stopping time or the choice of a date of exercise compatible with my financial information, I want that when I will take my decision, okay, to exercise at small t, okay, I will do it only using the financial information until time t. This is the meaning of this property here, okay? So it tells you that when you are at time t equal to 0, okay, the way that you will exercise your option is not known, okay? So you have a random variable, but a random variable that will take a particular value, okay? That will take the, that will choose a particular date in the set of the possible dates, only taking into account the information that will be available at these dates. I can't use more information than the one that I will have at this time, okay? So to choose tau to be equal to t will be done using only the information until time t. Okay, so I denote by t0 the set of all the stopping times, and I denote by capital T of small t the set of the stopping times that are greater than t. And of course, okay, with my notation here, if you are a stopping time greater than t, you are, of course, a stopping time. Okay, so I have this one. What is more, I can say that what is the set of the stopping time that are greater than capital T, okay, since my values are in capital T, okay, in this set, I have a single stopping time that is, okay, the stopping time tau equal to capital T every time, okay? So in T of capital T, I have a single stopping time that is the stopping time tau equal to capital T, okay? A single element that is tau equal to T here. Stopping time, that's the constant stopping time equal to capital T. Okay, so when I have an American option here written in its actualized way, okay, and if I have a stopping time, I denote by x tau, okay, the payoff of this American option that is relative to tau. Okay, so if I take tau as the decision of exercise, okay, if I take this decision at time t equal to 0, tau will represent what I will do in the future in terms of exercise, and what I will obtain. I will obtain the payoff x at the time where I will exercise. That will be for me tau, my random time strategy, let's say. Okay? So that's why I denote x tau, the payoff relative to tau. Okay? And keep in mind that from what you know from the course of stochastic calculus, x tau here is a random variable. Okay, xt is a stochastic process that is ft measurable. Tau is a stopping time. So using the law of total probability, you can prove that x tau is in fact a random variable with respect to f capital T. Okay, it's very basic to write, and you just have to write, I can write it this way, that x tau belongs to A can be written as the union of xt belongs to A intersected with tau is equal to T So it's not the law of total probability, but just the fact that here I have a partition of the universe. These events here are a partition of the universe, T from 0 to capital T, okay? So this one being equal to this one, okay? Here I have something that is in F small t. I have here something that is in L small t. So the intersection is in L small t. F small t is included in F capital T. So they are all in F capital T. And so their union is in F capital T. That's why X tau belongs to A, belongs to F capital T. That is the meaning of the fact that X tau is F capital T measurable, okay? So I denote by W tau the maximum of the expected relative payoff given Ft over all the stopping times that are greater than T. And I denote by Wt plus, okay, the conditional expectation under Q of Wt plus 1 given Ft, because I have something here, okay, that is, so Wt plus 1 is Ft plus 1 measurable, okay, and this one is the best approximation of Wt plus 1 in terms of Ft measurable random variable, okay? So here, okay, it's, you try to maximize your payoff, okay, at time t, with respect to all the possible choices you can do at time small t that are to choose among the stopping times that are greater than t. Okay, and we have the following proposition. Okay, so I have my definition here. Okay, I have the following proposition. Then we can prove that W capital T is equal to X capital T, and that Wt fulfill this one. In particular here, this is the max of xt conditional expectation under Q of Wt plus 1 given Ft. But as you can remark, in fact, previously, we have seen together that the price of an American option fulfill this one, U capital T is equal to X capital T. So I have the same terminal condition for U and for W. And I have also that Ut is equal to the max between Ut and the expectation under Q. Oh, excuse me. It's not Ut here, it's Xt. Conditional expectation under Q of U T plus 1 given Ft. And you see that U fulfill the same recursive relation than W. Since they have the same terminal condition, necessarily they are equal. So it means that, in fact, the price at time t, or the actualized price at time t of an American option, okay, is not the conditional expectation of the final payoff given Ft, but it's something that is not very far. It's something that is the conditional expectation, or the maximum of the conditional expectation given Ft of the expected payoff, the maximum being taken, okay, over all the stopping times that are greater than t. In the case of a European option, I have this one for the price, because, okay, in the case of my European option, I can only exercise it at capital T. In the case of an American option, if I want to find the price at time small t, I consider this conditional expectation, where here, instead of having the final payoff, I have the relative payoff relative to any stopping times greater than t, and I have to do the maximum over this stopping times greater than t. Okay, so we are not very far, but we have to maximize over by the set of all the possible strategy of choosing a date that is represented by the notion of stopping time. Okay, so I have another characterization of the price of an American option in terms of the maximum of conditional expectation of the relative payoff maximum that I take over, okay, sets of stopping times. And what is more, if I continue in the proposition, here I said that my price, in fact, because here, if I have small a, Wt is equal to Ut here. So the price is in fact attainable by a particular stopping time that is tau t star, okay, that is the one that allow me to reach, okay, the maximum in this expression, okay. There is one that allow to have the maximum here, and this one, in fact, has a particular expression that is the optimal stopping time greater than t in order to exercise my American option is given by the minimum of the t prime greater than t, such that, in fact, the intrinsic value of my American option is equal to its price, okay? So you have here a theoretical expression of what to do if you are at time small t in order to exercise in the best way your American option at a future date, okay? It's what you have to do here, okay? What you have to do here. But unfortunately, okay, so here I have a theoretical expression, but how to obtain this one in practice? In practice, okay, if I want to obtain this one, I have to approximate in general, okay? And it's a topic that is completely out of the scope of this course, okay? That is the topic on, of course, more mainly focused on American option, okay? So just say that I can express the price as a maximization program over stopping times. It's exactly what I have proved here, what I said in the proposition small a here, and say that these optimal stopping times may be expressed a priori explicitly. So I have a theoretical form for them, okay, but in practice, okay, complicated to obtain. And depending on the framework, okay, if you are in discrete or continuous time, because in continuous time you have exactly the analogous of this proposition here, then you may have, okay, some strategies in order to approximate these optimal stopping times. Okay, so I won't do the proof of this proposition in this video, okay, because my little remark concerning stopping times and American option is out of the program of this course, okay, for the final exam. But if you are interested in, you will have it in the lectures note, okay, and we'll be able to discuss about it. If you have some question about the proof, okay, you will see that I will do in the lectures note only the proof of this one, because I don't want to use too much results concerning, okay, stopping times and martingales, okay, so I do the proof for this one, and the proof of this one is a nice exercise concerning stopping times, okay, so you can do it in order to train with respect to the exam of stochastic calculus, for example, okay, and we will discuss about the proof of this one if you have some question, okay, in the next live session. Okay, so it closes the course concerning arbitrage theory, okay, and okay, the live session will be from now on devoted to your questions. So see you, bye-bye.